Hi, everyone. So my name is Emilija Perkovic. I'm an acting assistant professor at the University of Washington. I am also likely chairing this session. And today I will be giving a talk on identifying causal effects in maximally oriented, partially directed acyclic graphs, or MP-DAGs for short. So the goal of this talk is to essentially introduce identifying total causal effects of X on Y and how you can do that from observational data. Now, one thing that I will mention at the beginning is that throughout, I assume that there are no latent variables. Generally, so what's the total causal effect? So it's some change that happens in the response due to an intervention that sets some exposure variables X to a fixed value X. And we want to estimate this from observational data, whereas this is usually the setting that you have in randomized control studies. And the main challenge here is the fact that this interventional distribution of the response is different from an observational distribution of the response, or even an observational distribution of the response conditional on this X. So I need to introduce some notation. Throughout the paper, I rely on graphical models, specifically directed acyclic graphs, to represent distributions of variables, essentially. So in a directed acyclic graph here, I assume that each node essentially represents one variable in the system. And I will say that a DAG is causal if all observational and interventional distributions factorize according to this DAG. So here in purple, you have an observational distribution, this f of b x, y, and you see that it decomposes according to the DAG in terms of y given its parents, x given its parent, and so on. Then the interventional distribution of this data decomposes according to a mutilated version of the DAG, where you essentially cut everything into X because now X is fixed. And this interventional distribution factorizes in terms of these observational factors that do not include X. Okay, so what is then a causal effect? So a total causal effect is generally some functional of this interventional distribution of the response. So it could be this difference in expectations, it could be an odds ratio, risk ratio, whatever you prefer. So we say that this total causal effect is identifiable from observational data if this interventional distribution of the response can be uniquely computed from an observational joint distribution of the data. Right. So now you know, given the previous slide, that if I give you a causal DAG, then every total causal effect is identified. Since this f of y to x is just an interventional distribution of the response, right, you can just integrate over the interventional joint distribution. So you integrate over everything that's not in x and y, and you know that the interventional joint distribution factorizes in terms of those observational factors. So that seems to solve our problem for DAGs. Now, the main issue here that I'm tackling in the paper is the fact that generally you cannot uniquely identify a DAG from observational data. In fact, if this is your true causal DAG, and you assume, of course, no latent variables, then at most what you can learn from observational data without making additional assumption is something like this. Now, this is a graph called the graph that belongs to the class of completed partially directed acyclic graphs, or CPDAG for short, and it contains both these directed and undirected edges. And the undirected edges here mean that we are unsure about these causal directions. We don't know if X1 causes A or if it's the other way around. So essentially, this graph is a summary graph that represents an equivalence class of DAGs that contains the true causal DAG, but we don't know which one it is. Now, if in addition to observational data, you have some background knowledge, say from experts or some other restrictions that you can include as directed edges, you may end up with something like this. So here, the blue edges are background knowledge edges. So this graph is a type of maximally oriented, partially directed acyclic graph, or MP-DAG. And this graph class is very general. It also subsumes CPDAGs and DAGs, which is why I focus on it in the paper. So you can see that in this DAG, we have fewer undirected edges than in the CPDAG, meaning that the equivalence class of DAGs represented by this MP-DAG is smaller. Now, if this is something we can learn from observational data and background knowledge, the question is, when can we identify total causal effect in something like this? Meaning, when is the total causal effect the same in all of the DAGs described by this MP-DAG? So there's, of course, some graphical criteria that already exist on this, and I'll just list two kinds. So the generalized adjustment criterion can be applied to all three graph classes, so to DAGs, CPDAGs, and MPDAGs. It is sufficient for identification, but it is not necessary, meaning that it might miss some identifiable causal effects. I also just want to mention that all of these adjustment criteria built on Pearl's backdoor criterion, which you may be familiar with. The other criterion that I will mention is the G formula, which is a necessary and sufficient identification criterion in DAGs. And here I've given one example of this G formula, right, where we have this factorization of the interventional joint distribution, and we're simply integrating over everything that is not in X or Y. So the goal of my paper was to kind of give a generalization of this result to CPDAGs and MPDAGs, and so I've called it the causal identification formula. So this formula looks something like this, and I will not explain it in detail, but just to mention a few things. So the part in purple is a necessary condition for this causal effect to be identified in the first place. And then in blue, we have this decomposition into an observational distribution. So you can see that this decomposition looks very much like the G formula, except that this set S that we are now integrating over is the set of all nodes or variables that have a causal path to Y that is not through X. And you can see that the factors in the factorization are, first of all, sets and not just single nodes or variables. And also this set represent a decomposition of the set S into connected components in the undirected subgraph or MPDAG. So let's see how we can, for example, find this formula in this MPDAG, right? So we're interested in f of y given do x1 and x2. So first we find the set S. So we find ancestors of y not through x. So first to do that, we remove x, and then we see that A, B, C, and D are ancestors of y. Next, we want to partition this set S in terms of the undirected connected components. So here in the undirected subgraph, we see that the components are this B, C, D, A, and Y. And then finally, we can write out this causal identification formula by just taking all of these partitional components and given their parents, right? So you have Y given its parents in the MPDAG, A given its parents, and so on. All right, so that's kind of the highlight of my work. If you're interested to know more, I'm happy to answer any questions. Thank you. Finished in less time. Well, thank you for taking the time to join all of these videos together.